Oh, do you have the Zoom link? Okay, I will log in.
Okay. Hi everyone. I'm Shubhansh. I'll talk about our work reinitializing weights versus units for maintaining plasticity. This work was led by Fernando, but he couldn't come because of visa issues, so I'm giving the talk. Uh, and this is in collaboration with June and Rich. Okay. So the key contribution of this work is this new algorithm, which we call selective weight reinitialization, and this is designed for maintaining plasticity. Now, a quick outline of the talk. I'll just first talk about what is continual supervised learning and loss of plasticity, and then other selective reinitialization algorithms and how this algorithm uh, connects with the rest of the literature. Uh, and then I describe the selective weight reinitialization algorithm and then some experiments. So supervised learning, as we all know, is the setup where you have a learning system that receives some data and it learns to make predictions. And the goal is to learn some function that maps the inputs to the outputs while minimizing a loss function. So you can think of the classic MNIST where you have images of digits labeled from 0 to 9, and there is a corresponding label for the digits. So when you have continual supervised learning, you have a sequence of such data sets. Uh, and the key idea is that these data sets or tasks are non-stationary, so they're changing over time, and you have to keep learning new things. So one simple example is you start with the MNIST data set, and then you permute all the pixels in a certain way. So you have this permuted MNIST problem, and then you can keep adding these permutations, and you can have a sequence of such tasks. Uh, and the goal for these experiments that I'm doing is to design algorithms that can perform well on the current task. So I'm not focusing on forgetting at the moment. The goal is just to see if we can design algorithms that can learn on the current task. So yeah, so the permuted MNIST problem, you can make a continual supervised learning problem by making a sequence of such tasks, where on the first task you have some permutation, and then on the next task you have a different permutation. Uh, some important things to note here is that we use the same random permutation for all the images. That ensures that the mapping between images to labels is preserved. Each task is of similar difficulty for a feed forward network. All you're doing is permuting the pixels. And to measure the performance, we are just measuring the online performance, like the data point that's given to the network, how well it's doing on that. Uh, if you just train vanilla stochastic gradient descent with a feed-forward network, what you see is something like this. Initially, the performance improves, then it plateaus, and then it drops. This is the classic example of loss of plasticity, where the system is losing the ability to learn. It performs well initially, but not after some time. Okay, so a class of algorithm that has been proposed to mitigate this phenomena are based on selective deinitialization. What does this mean? It means that you carefully select parts of the network that you think are not uh, contributing much or have lost their plasticity, and you reset them because you know that the initial distribution was good and that was allowing you to learn. So you can imagine that this is some network where when you reset, you can reset the entire network. That's one strategy that's used. You can also reset some selected layers that are probably slowing down learning. You can also find some units that are dormant, and then you can reset them. Uh, and you can also just find arbitrarily located weights that are not contributing to learning, and you can reset them. So there is this spectrum where you can think of it like you start by resetting the whole network, then layers, then units, and then arbitrary weights. So essentially, uh, all these three of these have been studied in the literature before, but the selective weight, like finding weights and resetting them, that has not been studied. Uh, and that's the contribution of our work. So I'll just give you some idea of how to think about these algorithms. So when you're reinitializing weights, you have to think of these three things. First is a utility function. You want to have a measure which tells you like how useful a weight is, right? And then you have to find this pruning function that determines how many and which weights do you want to reset. And third, you need a reinitialization method that determines when you're resetting a unit, how exactly are you going to reset it. So I'll give a couple of choices for all of these so we get an idea of the complexity that's associated with designing such algorithms. So one thing you can do is you can have a magnitude-based utility that's sometimes used in the pruning literature, where you just find the weight that's large, that those are small, and then reset them. And then you can have this gradient utility. What it is, it's the product of the weight times the derivative of the weight of the loss with respect to the weight. This can be calculated using a mini batch. If you are familiar with the literature, you'll know that this is a first order approximation of the change in the loss when you remove this weight from the network. Okay. Now, if you want to design pruning functions, there are a couple of possibilities. First is proportional pruning, where you prune a proportion of the weights. For example, you have these weights that are sampled from some distribution U, and then you have this hyperparameter K that's like the proportion of weights that you're going to reset. So if it's 1.1, then you're resetting 0.1 of the weights, so 10% of the weights. Then you can also have threshold-based pruning, where you're going to prune all the weights whose utility fall below a certain threshold. So you can have all the weights, you can compute the average utility, and then you can select indices whose utility is less than K times the average utility. So K can be like 0.1. So if your utility is less than 0.1 of the average, then you reset those. Similarly, for when you're trying to reset, there are a couple of interesting choices. First, you can sample weights from the initial distribution and randomly reinitialize. And second, you can do this mean reinitialization, where you can reinitialize to the mean of the initial distribution. So that'll be like you just set the value to 0. So the new weights can be set to 0, they can be set random. So as I said, there are all these 8 possibilities associated with 2 different choices. There are more choices, but just to give you an idea, I'm just talking about these 8 choices here. So when you do an initial assessment, remember this is the base system that's just doing vanilla stochastic gradient descent. We know that L2 in this problem can be very effective, and similarly shrink and perturb is very effective. Shrink and perturb is L2 regularization plus addition of random noise at each step. Now there are 2 other lines. The yellow line is our algorithm when you're setting new weights to 0, and the blue line is the same algorithm, but you're randomly resetting the weights. What you see is that, oh, this performs fairly well, and this is using the proportional pruning that I described earlier. And similarly, you can see what happens when you use threshold pruning instead of the proportional pruning. Similar results, the mean reinitialization doesn't work. Resample initialization works. So the takeaway from this initial assessment is that not every setting of weight reinitialization is going to be successful. The most effective strategy is you use gradient utility with threshold pruning and reinitialize the weights randomly. If you use proportional pruning, that's also effective, but it doesn't perform as well. Okay, now we do a slightly larger scale experiment. We use the CFAR 100 dataset using the incremental, and we use a class incremental setting. So as you all know, for example, we start with first 5 classes. The network has to classify these 5 classes, then 10 classes, and then we increase up to all 100, right? So a few important things on how this setting is different than what's commonly studied. We train on data for all existing classes. So for example, when we are on these 10 classes, we're training on the data of all 10 classes, not just the 5 classes. So this isolates the problem of forgetting, and we can just focus on if our system can keep learning. And the measure of performance is the accuracy on the test set of all the classes that we have available. So initially on just 5, then just 10, and at the end, all 100. And we're going to use a vision transformer with 40 million parameters on this case. So a vision transformer has a bunch of components. One interesting one is uses layer normalization. So if you are familiar with layer norm, or if you're not, this is what it does. You have the output of a hidden unit, and then you subtract the mean that's calculated for the layer. You divide by the standard deviation, and then you have these two parameters, gamma and beta, which are learnable parameters that scale and shift the output. And then epsilon is a small number. Now there are a bunch of choices when you are training using layer normalization regarding regularizing this gamma or not. So if you do regularize it, what you end up seeing, so in this plot, what we have is the magnitude of gamma over time. The pink line is when you reset the network every time you get new classes. And the blue line is when you're just training incrementally. And what you see is that the value of gamma drops dramatically. And this is indeed associated with a sharp drop in performance. Um, so this is the network trained from scratch. So if you are not losing any plasticity, you would do as well as the pink line. But because the blue line does not do as well, it loses about 10% in performance. That becomes problematic. So what can we do about it? The issue is that gamma is going to zero when you're regularizing. Sometimes you don't regularize. If you don't regularize, then you see a lot of overfitting and you still don't do well. The solution is somewhat simple. What you can do is you can reparameterize gamma as 1 plus gamma. So when you do regularize gamma, it goes towards 1. The scaling parameter goes towards 1 instead of going towards 0. And then you see this performance. So there are two new lines. First is the gray line, which is when you're resetting and the network has this reparameterization. It always seems to do better than if you were regularizing towards 0. Even at the end, when you're just training on all 100 classes, you see a performance improvement with this reparameterization. And the black line is when the same network is trained incrementally. And you see that it performs better initially, but over time it dips below the gray line. And by the end, the performance is a little bit worse. An interesting thing to note here is that there is this sharp drop at the end. What's happening is out of the 20 runs that we did, in one of the runs, the network collapsed at the end. But when you just do 5 runs, you don't see this behavior, which I think is an important thing. And it tells us that, we need to really do 30 runs or more than 3 runs. Otherwise, these things can skip from our experiments. Like we did not notice initially that there was this collapse at the end. But when you do sufficient runs, you start to see, there is this collapse that's happening at the end. Yeah. Okay. So now I'm just going to plot the same thing, but with reference to the resetting baseline. So essentially, I'm just subtracting all the values from this gray line and seeing how the performance is compared to this gray line. So yeah, if you just take the reparameterized layer norm and then train it incrementally, you see the sharp drop. And if you don't have reparameterization, then you have a dramatic loss of plasticity in this case. If you use shrink and perturb, it performs fairly well. At least it doesn't collapse at the end. And if you have selective weight reinitialization, then it almost fully fixes this plasticity loss issue you are doing about as well as the resetting baseline. And if you compare with the other two algorithms, so continual backprop and redo are, as I was saying, our algorithm reinitializes at the level of weights. These algorithms reinitialize units in a network, but that unit resetting does not make sense when you have attention layers. So those algorithms do not do anything, and they also strongly suffer from this collapse phenomena at the end. So in summary, we have developed selective weight reinitialization algorithms, which reinitialize least useful units. We studied different settings of selective weight reinitialization and found the ones that are successful across a variety of network architectures. This was the only algorithm that maintained plasticity across a range of settings and avoided learning instability. And it's very easy to apply to any arbitrary architecture. You can just have a few lines of extra code with your optimizer and you can do this. So it's very easy to use. Some key limitations are that we only focus on supervised learning with non-stationary inputs. But in, for example, RL, you can have systems that have both non-stationary inputs and targets. So one direction for future work is to explore how these algorithms do in RL. And we did not study the problem of forgetting. And I think it is important to study, especially for these types of algorithms where you are explicitly deleting some weights and resetting. So you're explicitly forgetting some information. So it's important to study how these algorithms affect the forgetting issue. And yeah, in general, we want to develop better algorithms with new utility functions, pruning functions, and reinitialization methods. Thank you.
Hey, thanks for the presentation. I was wondering, like, when you reinitialize weights, the initial initialization scheme that you had, like, when you started, and then when you reinitialize, like, I don't know, n steps down the line, like, your weights might have drifted, the distribution may have changed. Like, have you done any analysis on, like, whether to reinitialize with some sort of running estimate of the weight distribution versus the original one that you used at the very beginning, and whether it makes a difference at all?
Yeah, that's a good question. All we did was reinitialize with the initial distribution. In general, what can happen is the weights can become either too large or too small. And if you're just again resampling from that distribution, that might not be effective still. But yeah, that's a good point. I think it's worth looking at how the drift is actually happening, how much the mean and variance are changing.
Hi, thanks for the talk. So you mentioned that some of these other methods were collapsing on the vision transformer because you basically were resetting the weights to 0. Did you also study in these other methods resetting their weights in a different way, similar to your method, to understand if they were capable of regaining that performance?
So just to be clear, in the transformer experiment, we didn't reset the weights to 0. We reset by sampling from the initial distribution. Right, and the collapse was happening because of this quantity. I did not present originally. So what this is the median weights in the last attention layer, like the key query weights. And you can see that over time, over training, these weights just dramatically decrease. And because these are multiplied with each other, you underflow the minimum floating number. And for some reason, that seems to happen when you have this reparameterization on layer norm. When you start regularizing layer norms, for some reason, the weights just keep dropping, and we don't really know why that's happening. Yeah.
Any other question? Okay, let's take our speaker again.